Okay, this one lecture sheet 5. So far, we talked about the fluid property, right? Then we start with some law, little law of viscosity, then cohesion, then adhesion property of the fluid, then Newtonian non-Newtonian fluid we learn. Then we start with some derivation that how much will be pressure at a certain depth of the fluid. Then we derive how we can measure the pressure by analytically by formula P equal to H rho Z, right? Then we learn how we can measure the pressure in a certain container or pressure difference between two container or pressure difference between 2 points of a pipe by using pressure gauge and also by using manometer. So in manometer, how it is worked actually by the pressure difference by a vertical column of fluid. And we already derived the pressure balance equation to figure out the deflection of the manometer. And from that manometer deflection, to figure out the difference in pressure. And we solve some problem. Then we talk about the hydrostatic pressure in a mechanical structure that's submerged in water or any other fluid. Then we also talk how the a body stabilizes when it is submerged in the water, like a boat or ship. Also, we figure out when a body will be sink and will be float in the water. All those things we talk about the static fluid. That means fluid is not moving. But this chapter will talk about fluid kinematics. So kinematics means includes some force and some, not some, I would say velocity of the fluid or motion of the fluid. So it's no more static, right? But here we'll also apply the your law of inertial mechanics. For example, F equal to ma. Applied force externally on the fluid will be equal to the mass into acceleration, which is second law. Okay. So to learn the new chapter about fluid kinematics or about to know the motion of the fluid, we need to know some terms, some criteria. Okay. To get the not in-depth but fundamental idea about the fluid kinematics. So let's see what we have. What is the fluid kinematics? It's saying the fluid kinematics is the study of how fluid flow and how to describe fluid motion without considering force and moment. That right over here will not describe, will not talk about the force and moment working in the fluid. It's a without considering force and moment, how we can describe the fluid flow and motion of the fluid. For example, you like to figure out that there is a waterfall. From the high hill, water is falling down, then water flowing through a canal or river bed. So how those water will flow? For example, a fluid particle fall down from the fall right over here. He might be flow directly, straight line, or he might flow coming right over here, might come in a zigzag way. Okay. So all those things we will study in this chapter. So what is the assumption that we will not consider the force and moment? Okay. So there is a two term used to describe the fluid in motion. Number one thing that one is kinetics, other one is kinematics. So kinematics, we already said that we will not consider the force and motion of the fluid without considering. So what is then kinematics? It's saying it involves position of a fluid particle and velocity and acceleration, but not the force. Fluid kinematics, it describes the position, velocity, and acceleration, but we will not talk about the force. Fluid kinematics describes how a fluid particle translate, distort, rotate, and how to visualize in a flow field. Flow field means in a flow. Now here two terms is used, is translate, distort, rotate. So for example, a fluid particle, if I think a fluid particle is rectangular and say coming, this is my south side and this is north. So he is coming from the north to south through a river. So fluid particle might be any type, right? So I am saying this is a small cube, rectangular. If I only think 2D, then it will be like that, right? That full rectangle or square. So he's flowing in the river. On the way, he might become, after a few seconds, he's coming right over here, then coming right over here. And gradually he's used. So this motion, you see, this fluid particle is called translation. It just move from one point to other point without making any rotation. Rotation means rotation around CG of the fluid particle. It's this fluid particle came in right over here. I just make it a bit bigger, came in right over here. Then after a few seconds, he came in over here. When he came in over here, then what does it mean? That means still it is a cube, but when it's coming over here, then it's rotate about his center of gravity. That means it is rotation. And what is distortion? Fluid particle came in over here, then his length is sense. Side is sense. Size get bigger. So that is called distortion or distort. Okay. And we will check it that when a fluid, there will be rotation in the fluid, and when there will be only translation. And when you travel in a river, especially in rainy season, you might see in some location of the river, the water is just rotating. Okay, so we'll figure out under what condition a fluid particle might be will rotate, and how we can figure out mathematically. Okay, then we'll see over here. Now, kinetics. What is the kinetics over here? It says the science which deal with the action of forces in producing or changing motion of the fluid is known as hydrokinetics or simply kinetics. The study of fluid in motion involves consideration of both kinetics and kinematics. So if you like to study the fluid motion, you need to apply both things. Okay. Right, you see the fluid kinetics and how fluid particle is translating or rotating, or it has a linear strain or shear strain. Okay. So if you look in the first figure, a rectangular fluid element, and he just travel from one point to other point without any deformation. Actually, this is looking, we are 2D view. Actually, this fluid element will be like that. Okay. So after he came in over here, still his size and shape is not changing, but his position is changing from one point to another point. So this type of movement of fluid particle is called translation. Now, what is the rotation? My original fluid element is a square. Say it was right over here. So when he came in over here, then he make a rotation. That means his position is coming like from here, like this one. So what does it mean? His shape still remain the same, but he make a rotation, rotate a little bit. That is called rotation. Now in the bottom is called linear strain. What is the linear strain? A fluid element is right over here at a certain time, say after few moment or 3 seconds or millisecond, is coming from that point to this point. So what happened over here? That means his shape is changing, dimension is changing. So that is called, he remained, it was a square element or cube, but when he traveled from, let's say this is point A, he traveled from point A to point B, then his shape is changed. His shape is coming like this. So what does it mean? Actual rectangular shape is still there, but one dimension is changing. So that is called linear strain. Okay. Other one, shear strain. So what is the shear strain? That means fluid particle remain right over here at point A. After few moment, same fluid particle is came in point B. When it came in point B, then his shape is changed. That means it's coming so what does it mean? I will clearly explain just 1 second. Like this. So what does it mean? That is called shear strain. What is the shear strain? Angular deformation. because this side was straight, but his angular deformation changing this much. Similarly, this edge was right over here horizontal, but is moved anti-clockwise direction. And this one moved clockwise direction. So it happened like that. Okay. So by using these four criteria, we can figure out the when a fluid will be there will be in rotation, when a fluid flow will be smooth. Smooth means, for example, fluid element does not changing that much direction or shape. Say a fluid element right over here is passing straight right over here and passing one after another. But that is called a laminar flow also. But sometimes you see, say, is something floating in the river. Then this floating small thing, after certain time, he came in over here, then passing over here. Then next moment, hitting this fluid element. Then this one flowing along this direction, he is coming along this direction, again hitting this one. So this type of flow is called turbulent flow. For example, you have something is burning, okay, and making smoke like coil. From the coil, mosquito coil, you see some portion, the smoke coming out is flowing smoothly. But after certain distance, you see the smoke is getting mixed together and flowing in haphazard way. So this portion is called laminar flow, and this portion is called turbulent flow. But we'll explain you later on more better that how the flow become turbulent and when the flow become laminar. Okay. They say because fluid are in constant motion, motion and deformation are described in terms of rate. Now, this displacement, like in every case, fluid is moving from one point to another point. So obviously, it takes some time, right? So a fluid particle is right over here. After 2 seconds, for example, coming right over here. So how much distance is traveling? So he's traveling from CG to CG, this much distance. Within how many time? 2 seconds. But it might be millisecond. So you can figure out the rate, that means total displacement or distance traveled by the fluid element divided by the time. So you will get velocity, right? So that is called velocity rate of translation. Similarly, you can figure out at what velocity fluid element is rotating. So that is called angular velocity or rate of rotation per unit time. Then right, this one, your fluid particle at a time right over here, but after certain time, fluid particle came over here. So you see linear strain happening over here, but it takes some time. I will figure out the time, how much time take to move from point 1 to point 2. So that is linear strain. So rate of linear strain you can figure out. Similarly, a fluid element remain this point at time t. At time t plus delta t, that means within millisecond or 1 second, this fluid element is coming right over here, and his shape is changing. So in that case, how we'll figure out the you figure out that how much take time to rotate this, not rotation, angular deformation of this fluid. Okay, so it's called shear strain, and this shear strain, fluid element was right over here. When he came in over here, then his shape changed by angular deformation. So you divide by the time, how much take time to travel from one point to another point, divided by the amount of shear strain. Shear strain, how will figure out the shear strain? Amount of angular deformation, this much angle. Similarly, angular deformation right over here. From that deformation, that angle divided by the time, it will get rate of shear deformation in the fluid element. Okay, now the motion of a fluid element depends on how many variables. So for example, you are even in a room. So fluid particle entering in your room right over here at time t. But within second, the fluid particle is traveling through other window and get out from the room. So he traveling from one point to other point, how much time he take? He take delta t, right? And you see, he is not traveling in the horizontal plane. That means his position along 3 axis might change. So this v of velocity of the fluid particle is function of x, y, z, and t. That means velocity is function of space and time. Similarly, if you like to figure out the positions of the fluid element, you see its position is changing. He coming over here after a few seconds, right over here, and finally get out from the room. So every point, if you like to say the location of the fluid element, then you have to say x coordinate, y coordinate, z coordinate, and also you have to say what is the time, because his position is changing with respect to time. So position also function of 3 vectors, x, y, z, and t. Okay, now how you can observe a motion of a fluid element? There is 2 methods normally used. Number 1 is called Eulerian method, right over here, Eulerian method, and other one is called Lagrangian method. So we need to know what is these 2 methods and what is the difference between these 2 methods. Saying in the study of fluid flow, it is necessary to observe the motion of fluid particle at various points in space and successive instant of time. Space means function of x, y, and z coordinate, and also successive instant of time. For example, if you are, say, there is a river flowing like that, and in the river, in the evening, you are sitting in the river, and something is coming from this side to say from this is just north, heading from north to south, or flowing along this direction. You are sitting over here, right? So you will see that there is a fluid element right over here. How he is passing? So he coming over here, he coming over here. You observing that fluid element, that how this fluid element is passing through the river. So this is your one observation. Your position is fixed. From this position, you are looking the how fluid element is flowing throughout the river. This is one option. Other option, that you remain right there and you are looking only the fluid element passing this line, that how they are passing certain instance. That means you are not looking the whole path of the fluid element, just looking on from a certain location, that how fast or how slow the fluid element is passing through my position. Okay, so there are two criteria, the how you can observe the motion of fluid particle. For example, you are sitting right over here. This is the road. Okay, there is a crowd demonstration in Bangla missile, and your friend, he is in the crowd right over here. Okay, he's in the crowd. So from here, you can observe him. The demonstration going along this way. So how he moves with the demonstration all the way to until get out from this position. So your eye only on him, that how he is flowing with the stream of the demonstration. This is one thing, right? Another thing, you just sitting over here, then you are looking that every second how many people passing through this line or through the piece or over this. You just counting that number. So this is one observation, and these two observations you see is not the same, is different. So similarly, in the fluid element, if you observe the motion, then there is a two method. One is the Lagrangian, other one is Eulerian. So what is the Eulerian method? It's the flow quantities such as velocity, density, temperature, pressure is a function of space and time at a particular point without referring to any individual identity of the fluid particle. So you are looking at a certain point, that what is the velocity of the fluid, what is the pressure of the fluid. That means if there is a river flow, so at a particular point, say sitting right over here, and right over here you are measuring the fluid velocity, pressure, density, everything. Okay, so that is saying the space and time at a particular point without referring to any individual identity of the fluid particle. Eulerian method is most commonly adopted in fluid mechanics, and in this method, you see velocity, and fluid velocity has three components: U, V, and W. W is the velocity component along z-axis, and also all of the component of velocity x, y, and z direction is function of time. Okay, other method, Lagrangian method, it's saying flow quantity are described based on behavior of each individually identifiable fluid particle moving through the field of interest. That means, I give example that your friend in the demonstration with a red shirt, and you are keeping eye on him, that how he is flowing throughout the crowd during the demonstration. So that kind of observation is the Lagrangian method. It's a flow quantity are described based on behavior of each individually identifiable fluid particle moving through the field of interest. That means moving through the flow. And how fluid velocity become function of X, Y, Z. I give you example that a fluid particle entering through your window, then it will travel around your corner due to the fan, then finally leave through the other window. So that means the fluid particle traveling in all three axes, X, Y, and Z. Similarly, in a canal or river, a fluid particle right over here. So you think this is X-axis, this is Y-axis. So after certain time, this fluid particle came in over here. That means he's changing his distance along X and Y axis with respect to time. And you'll see he came in over here, then he's moving a little bit down. And in the river, you will see that some floating things is floating, he's passing, then due to the vortex, he is going down. So that means his dimension is changing along the depth, that means along Z axis. So that's why you see all the velocity component, the U, velocity U, V, W, all of them again function of X, Y, Z, and T. So, right the difference between Lagrangian and Eulerian method. Lagrangian method is a moving reference frame. Your reference frame is moving because you keeping eye on your friend with the depth chart, and he is moving, right? You are looking to him, that how he is moving through the stream. So at one point he is here, and you will see next few seconds he coming over here, then coming over here, and he's dancing in the crowd, and finally he coming over here in the street, in the road. So he is moving through a path. So you are observing him, or observing a fluid particle through the path of the fluid particle. That is called Lagrangian method. Focus on behavior of fluid particle as they move with the flow. That means you are looking throughout the path of the fluid flow. And Eulerian stationary reference frame, you are observing a crowd from your base, that you counting, then how many people crossing this line in every second or every minute. That means your focus on a group of fluid particles at a particular point, that how they are behaving. So it's saying stationary reference frame, focus on behavior of group of particles at a particular point. That means you're just sitting at a space or point. From that point, you're observing the motion. Now, what is this application? Lagrangian and Eulerian method. There is a two type of flow, laminar and turbulent. Then fluid motion, how we'll figure out, how we'll solve. For example, you have a ball you're keeping over here, and if you describe the fluid flow, this ball you're keeping in the wind tunnel or keeping in the, then how will be fluid flow? Fluid is coming, say, coming this way, then it's move over the ball, then going this way. Then coming again, it's some fluid go this way. And gradually it will stop. Right? At a certain distance, then fluid will pass straight. So this streamline, how can we visualize? Say you have a ball and you keep it with a stand. Say stand, the ball has a stand. and you have fan over here. You start, so air will flow along this direction. If you are to keep some smoke generate right over here, then you will see how the smoke flowing over the ball. That means you can observe the flow. And this one also you can simulate in some software like ANSYS and SolidWorks might be covered, I'm not sure. These other software. In the software, how they figure out? In the software, they'll show the line that this is the path of the fluid particle. Flow will be like that. But how they calculate? There is a two method. Mathematically, either they solve this, use this one, or either this one. Okay. There is a in fluid mechanics lot of differential equation. By solving those differential equations, they figure out the flow pattern of the fluid and they give you the simulation on your computer screen. Okay, that's the example. So one software might be used this method, other one might be using this method. Depends on what type of flow and what type of software you are using. Okay, there is one term used in the fluid mechanics. It's called material derivative. What is the material derivative? So it's saying total derivative operator d by dt is a given special name. Is called also it is called material derivative. So a lot of time we use say y equal to x square plus xy plus p cube, because it is also function of time. How you can make the derivative? You can make dy by dx, right? You can figure out dy by dt. So right over here, this derivative dy by dt sometimes is called material derivative. Big D by dt expressed this way. Okay, just remember, big D by dt is called material derivative. It is the same as small d by dt. Right over here is the showing that say you have a function b velocity, and this velocity b equal to b of function of x, y, z, and time t. In that case, how you can figure out the dv? So dv, anyone, how you can figure out the dv? You can say dv divided by dt into dt plus dv divided by dx into dx plus dv divided by dy star dy. Then you will have dv by dz star dz. That way you learn from the mathematics class. Okay. Now, the both sides, if you divide by time dt, then what will get? You get dv by dt equal to dv by dt, right? You get dv by dt plus, you will get dv by dx into, now you see dx by dt is giving you a velocity component along x-axis, that means u, plus similarly you are getting dv by dy velocity component along y direction v. Then this one is getting you w, the velocity along z-axis is w. Okay, so finally you are getting this portion is getting acceleration. This is your acceleration, and this d, you see in the left side is total derivative dv by dt. We might say this one and this one same, is not the same because all them is del. That means partial derivative, and this one is the total derivative. So if you have a function that depends on x, y, z, 3 or 4 variable, then you can, this way you can figure out the total derivative of that function. You see velocity is the function of x, y, z, and t. How we can figure out the acceleration? So acceleration is equal to total derivative of velocity dv by dt, and by using this way we can figure out the acceleration, and after you solve you will get this one. Okay, so this is coming from the mathematics, so I just try to refresh your mind. Okay, and sometimes dividing this one is del operator. I think you already know from the mathematics. So this is the vector of partial derivative. So dy by dx, the derivative along x-axis, along y-axis, along z-axis, and all the derivative has vector component. And a fluid velocity of fluid particle, it has along 3 axes, x, y, z. So along y-axis, x-axis, y, and z-axis. Then how much will be the dot product? So value of dot product of curl V will be this one. Okay. Similarly, if you like to figure out what dt by dt, it will be this one. Okay, that means you see the acceleration derivative of velocity dv by dt, you can express in terms of this value dt by dt v into del t. Okay. Okay, so far any question, anyone? Hello, any questions? No questions? Okay, we need to know some definition. As I mentioned at the beginning of this class, that we are studying the new things, the motion of the fluid element or fluid particle. And we are not talking about the static fluid. We are talking about the fluid in motion. For example, if you like to observe fluid flow through a pipe, like in your house, fluid element passing through the pipe, right? Also, the gas is coming through the pipeline, and also water flowing in a river. So all those situations are example of fluid in motion. So you need to know some definition. Number one thing is steady and unsteady flow. What is steady and what is unsteady flow? Then what is the uniform flow? What is the non-uniform flow? one-dimensional, two-dimensional, three-dimensional flow. That you already familiar. That means if flow only in one axis, that is called one-dimensional. If flow have along two axes, then it's called two-dimensional. Similarly, if velocity of a fluid particle has three components, or it has a displacement along three axes, then you can say flow is three-dimensional flow. And most cases, if its flow is saying two-dimensional, that means we have only two velocity components, right? Along x-axis u, small u, and y-axis small v. And velocity w along z-axis will be 0 in two-dimensional case. In three-dimensional, you have all the three components. And one-dimensional, you have only one component, either u or might be v or might be w. Then you have rotational flow, irrotational flow. Then laminar flow and turbulent flow. So we will discuss later on that what is the laminar flow and what is the turbulent flow. Now we say steady flow. Fluid flow is said to be steady. And steady if at any point in the fluid various characteristics such as velocity, pressure, density, temperature, which describe the behavior of the fluid in motion, do not change with time. That means in a river, the fluid particle is passing certain velocity at this point. Say, if coming in the morning in the river bank, and you counting that what is the velocity of this fluid particle moving this line, You came in the morning, then came in the afternoon, then you came in the evening, and you see you have the same velocity. That means velocity is not changing with respect to time. That is called steady flow. If it changes with respect to time, that is called unsteady flow. Okay. So unsteady flow, fluid flow said to be unsteady if any point in the flowing fluid, one or all the characteristics are described, the behavior of the fluid motion change with time. So I give you only example of velocity. Fluid particle might have density, might have pressure. So all those velocity, pressure, density, temperature, everything is not changing respect to time, then it is called steady flow. If it is changing respect to time, then it is called unsteady flow. Okay. Now we'll say what is the uniform flow and what is the non-uniform flow. Uniform flow. When velocity of flow of fluid does not change in both magnitude and direction from point to point in the flowing field for any given instant of time, the flow is said to be uniform flow. If you look this figure on the right hand side, if I think about some fluid element, say some fluid element right over here, I pick up some fluid element. At the time, they are at the right over here. So this fluid element, after certain time, say 2 seconds, within 2 seconds, this fluid will travel only this much. This one only this much. The next one travel a little bit faster, and in the middle, all of them is travel same distance. That what does it mean? That means this flow is uniform flow. Almost all the except the wall, because the wall have less velocity due to the viscosity and the friction. That's why he travel less around the wall. But at the middle, all the fluid element, almost their velocity is same. So this type of flow is called uniform flow. And non-uniform flow, if you look over here in the left side figure, you see the fluid particle right over here is not traveling that much. But fluid particle right over here, he traveling from here to this much distance. And fluid particle right over here, he travel from here to here. And at the middle, he travel more distance. So that means each point, their velocity is not the same. So that's why this type of flow is called non-uniform flow. If the velocity of fluid from changes from point to point, then it's say velocity of flow field changes from point to point in the fluid at any given instant of time, then its flow is said to be non-uniform flow. Okay. All this type of flow, and you see right over here, there is a three types of flow, four types, right? Steady, unsteady, then uniform, non-uniform. Then there might be mixed type of flow. When it's saying steady, uniform flow, there might be steady, non-uniform flow, then steady, uniform flow. So, what is the example? Say you have a constant flow, rate flow in a constant diameter pipe. If you have a pipe as a fixed diameter, that means that will be steady uniform flow. Because its diameter is same, so all the fluid particle will travel with same velocity. So that is called, and velocity would not be changed respect to time. So fluid particle right over here, he travel this much, fluid particle right over here, he will travel say by same distance. If it is diameter is not changing. So that is example of steady uniform flow. Now, if you say add your pipe, 1 second. This is your pipe, but you are using a valve to control the flow right over here through this valve. Okay. You see, when you taking shower, you open the tap. Your pipe has fixed diameter, right? You are rotating a little bit, opening the tap. Then what will happen? Water will fall down through the tap. But all the water will have same velocity, but their magnitude will not vary depending on time. Because you just open a little bit, then you stop. Okay. Again, after you open more and stop, and fluid will pass through the tap with higher velocity, right? But say to opening your tap, it takes 10 seconds, for example, by your hand, from close to full open, right? So what happening? All of them have the final is close, no velocity 0. Then gradually you turn on within 10 seconds. So when it's 10 seconds, all the fluid will coming out through the tap with higher velocity. When it's 6 seconds, velocity will be less, right? That means at 0 time, velocity 0, time increasing, your velocity increasing because you're opening more. Gradually, when you are getting at the full point, that means opening full within 10 seconds, then velocity will be maximum. But each time, fluid particle will flow with the same velocity. So that is an example of unsteady uniform flow. It's either decreasing or increasing flow rate in a constant diameter pipe is the example of unsteady uniform flow. Similarly, when you closing, your bulb remain full open. Then when you are rotating the knob, then you open it, closing, right? The fluid velocity will be gradually decrease. So you cannot stop immediately. It might take some seconds, right? 20 seconds or 15 seconds. So within 20-15 seconds, your fluid velocity is changing respect to time, but at certain instant, say at 6 seconds, you stop. Then what will happen? Through the 6 seconds, all the fluid particle will travel at the same velocity. So that is example of steady, unsteady, uniform flow. Now, instead of constant diameter pipe, if you have taper pipe, for example, right over here, little bit wider cross section, but right over here, cross section is narrow. Then what will happen? Your fluid particle at the middle will travel faster, but at the side wall will travel with less velocity. That means velocity is not same due to the change in diameter of the pipe. So in that case, either you are decreasing or increasing the flow. You will see when you just open a little bit, your velocity profile of the will be like that. That means at the middle one will travel with the higher velocity, and gradually at the wall, velocity will be decreased because it is taper. But if it is constant diameter, then all the fluid particles will travel with the same velocity. So in that case, your velocity profile will be just like that. Let me see if I draw arrow. Velocity profile will be like this. Okay. So if a flow increasing or decreasing in a taper pipe, that is the example of unsteady non-uniform flow. Okay. Any questions so far? No questions? Okay. And so from here, from the beginning, what type of question might be in the exam? That what is fluid kinematics? What is the difference between fluid kinetics and kinematics? Then describe the rotation, translation, and angular deformation of the fluid element. Then I might say what is the total derivative of the fluid particle. Then what is the difference between Eulerian and Lagrangian method? Define Lagrangian method, how it is varies from Eulerian method. That might be the question from this chapter. Then definition, what is the steady flow, unsteady flow, what is the rotational and irrotational flow, laminar and turbulent flow. Then uniform, non-uniform flow. So from you need to know the definition of the is. Okay. Right over here, just giving a example that velocity always function of x, y, z, and t. And if it is two-dimensional, then you have only 3 variables because it has a time. And if it's steady, steady means does not depend on time. Its value is not changing with time. Then the velocity will be function of only x, y, and z, because magnitude of the velocity is not changing with respect to time. Similarly, in 3-dimensional flow, velocity will be for unsteady case x, y, z, and t. But it becomes steady. That means velocity does not change with respect to time, even constant. So in that case, your velocity will be function of x, y, and z. Okay. Similarly, for one-dimensional flow, this one for one-dimensional steady flow. Right over here, just giving an example of flow, of rotational flow and irrotational flow. So right over here, you see this one irrotational flow or translation, because fluid element, what is the path of the fluid element? It travels along this line, right? Or it might be travel again or come back over here. But each point you see the shape of the fluid element remain the same position. That means its shape remain the vertical, right? And it is not changing. It is not making any rotation. Overall path is making rotation, but it is not rotating with respect to his own center of gravity. So this type of flow is called irrotational flow or translation. If say a flow is said to be irrotational or translation if fluid particles are not rotated about their mass center while moving in the direction of flow. Okay. Then rotational flow. You look right over here, a fluid particle was right over at a time. It came in over here, over here, over here, over here. If you look carefully, you see, in every case, he rotated. Right over here, he rotated along this direction little bit, right? Then coming over here, still he has rotation. He came in over here, again he make rotation in opposite direction, becomes straight. So, irrotational flow is said to be irrotational if irrotational or translational if fluid particles are not rotated about their mass center while moving in the direction of flow. This example is this one. And rotational flow, a flow is said to be rotational if fluid particles are rotated about their mass center while moving in the direction of flow, like this one. It's called irrotational flow. Now, we need to see what is the laminar flow and what is the turbulent flow. A flow said to be laminar when fluid particles are moved in a layer. Laminar means laminar, one layer by other layer. With one layer of fluid sliding smoothly over adjacent layer, and there is no moment transfer in between the layer. Viscosity of the fluid play important role in development of laminar flow. You can easily observe the laminar flow and turbulent flow. Say you have two bottles. One is empty, other one is full of water. And you transferring the water from one bottle to another bottle. And if you put slowly and you see one type of flow, if you look the flow at the close to the mouth of the bottle, you see the observe that flow. Another thing, you are changing or getting some honey from a bigger bottle. Then you look to the flow. And that two flow is not the same. In case of honey, you will see, or say mustard oil, you see, or cooking oil, you see the flow is coming down very slowly, seems like they are in a straight line. That type of flow is an example of laminar flow. But in put water, you will not see that kind of line when you getting water from a bigger bottle by pouring. So laminar flow, this is the example of laminar flow. So in laminar flow, what is the example? That fluid particle is flow in a layer through this layer. This layer will travel a little bit low velocity because he is close to the wall due to the friction. If I took the lower one, that's showing the layer coming over here. Okay, but the immediately top layer of the fluid, he will travel a little bit faster because he'll try to hold him down, the bottom layer. Okay, travel a little bit faster. Then say at the middle, traveling with the same velocity, this one with the almost same velocity, and gradually moving to the wall, velocity decrease right over this much. But you see, the fluid particles, they are traveling with the same velocity and they are not mixing each other. This type of flow is called laminar flow, and it easily observable. You are, if you look to a flow in the river, sometime you see a lot of things floating in the river and going with the water, right? In the north to south, or all the river flow from north to south, right? So you see that a floating element in the river is right over here, and you see, observe 10 minutes how he's flowing. You see he's flowing with a straight line. He's not changing the direction. That type of flow is called laminar flow. And right over here, he's not changing the direction. So this type of flow is called laminar flow. But if this flow is changed, say this will particle right over here, in the next moment is coming right over here, and this one next one coming over here. What does it mean? That means every time is changing the direction. So if a fluid particle, say right over here, say all the fluid particles right over here, same line, entering in the pipe, then this fluid particle is supposed to go straight, but he is coming over here. And this one, say coming straight, right over hitting this one. So after hitting, he is changing direction. He might flow right over here, then he might flow coming right over here along this direction. So in case of turbulent flow, fluid particle not traveling in a laminar, and every time they are mixing together and flow in a haphazard way. Why it happened? There is a continuous collision between the fluid particle. So if there is a collision, that means when it is flowing, then on the way, it is hitting other fluid element. So if it's hitting other fluid element, what will happen? It is momentum is changed. MD, Vorbeck is changing. So that means you might solve this kind of problem that you have a one body, other body hitting this body with a certain angle. Then this body is traveling together certain distance, or they might be travel in different direction after hitting. This one this direction, and other body might be travel along this direction. Okay, so your momentum, that you use this kind of equation, that M1 V1, right? Or you say M into V, last velocity, momentum, into M1 plus M1 V1 plus M2 star V2, right? This type of problem you solve. That means your momentum is changed. Initially, they're coming both this velocity, but finally they're getting out this equal to M mean it's a M1 plus M2 into V. Then you can figure out the final velocity of the object after impact. So this way, in laminar flow, there is a continuous transfer of momentum. So it's saying that a fluid in motion is said to be turbulent when fluid particle moves entirely in a haphazard or disorderly manner that result in a rapid continuous mixing of the fluid leading to momentum transfer as flow. So there is continuously transfer of momentum in a turbulent flow. But in laminar flow, there is no turbulence. How we can observe? Just example I give you, that if you observe the flow from a smoke flow from a coil or from a cigarette, you will see the first portion. So this is the coil, and you will see the smoke is coming out, all of them passing, seems like in a line. Then suddenly they got haphazard, mixing together. So this portion of flow is laminar. Then it become this portion is turbulent. Now, flow visualization. How you can observe a flow around a object. For example, we design a submarine. And a submarine, if you look from the side, look like a pipe, right? Round pipe. So for example, like this type, but it have some fin at the top for communication purpose. Now, how flow will travel over this, the body of the submarine? How we can figure out? How we can observe? You cannot like design the submarine, you put in the water and you look. No, it's a big size. You cannot do that, right? But there is a scope of opportunity that you make the submarine with a smaller size, 1,000 times less or 100 times less, but shape remains the same. It's called model. By ship material, by wood, or you can make a foam. Then that one you put in the wind tunnel. You put in the wind tunnel, then air will flow. And if you generate some smoke, then you can see that how fluid flowing around the fin or around the body of the submarine. This is called flow visualization. Similarly, you design a sports car. It will drive, say, 150 miles per hour. Then you need to figure out that how will flow will travel over the body of the car. You see all the older cars, they have kind of box shape. But if you look the new car, their shape is more aerodynamic. That means they figure out that if you make the aerodynamic shape, then the air will easily flow over the car. That means it will get less resistance of the air. But you design a car, now how you will observe the flow, that you need to figure out the how air will flow over the car or under the car. Or you might say design a helicopter or design an airplane. So how you can look that flow. In that case, you have to make a model of the object. Then you can put that object in the wind tunnel. You flow the air, and before at the front section, you put some chemical to make the smoke. Then you can observe the flow. Say right over here is showing a flow over a ball. This is one option. Other option that if you use some software is called CFD. What is CFD? Computerized Fluid Dynamic Software. Okay. Using this software, you can look the flow pattern, that how flow will be over the object. So it's saying flow visualization is the visual examination you will see on your eye of flow field feature. It is important for both physical experiment and numerical solution. Numerical solution means by using some CFD tool like ANSYS, Abacus, Neston, Batman. Okay. While quantitative study of fluid dynamics, it requires advanced mathematics. So what ANSYS does inside the ANSYS, you make a model of the ball in the ANSYS, then you give the direction to the ANSYS that air is coming with 20 miles per hour. So show me the contour, how will be air flow over towards. What will do? You need to put some in the ANSYS. They have some data. They know what is the velocity of the density of the water or air, and you will put the what is the temperature. He'll figure out the radius of this ball, size of the ball. Then you are giving velocity. So in terms of velocity, figure out flow will be laminar or turbulent. He'll calculate inside. Then there is some mathematics, differential equation. He'll solve behind. Okay, you will not see in the screen. After solving all the differential equation, he'll give a result, and he will give a visual demonstration of the flow flowing over the ball. So actually, there is a advanced mathematics is going on inside the software. Okay, there are many types of flow pattern that can be visualized. Many types of flow pattern, both physically and experimentally, and also computationally. Computationally means you can observe in a software. The flow pattern may describe by means of streamline, stream tube, path line, streak line. So this flow pattern, how we can describe? There is a some definition. Number one thing is for those lines right over here is called streamline, and you see right over here that motion of fluid element along this streamline is passing in the straight line almost, right? But this one is not along straight line. It's a little bit different, right? That means this guy, this fluid element, it was also about this place, right? He moving along this line, this one also coming, following his path. What I'm saying, along this line, every line you see, all the fluid element is going through a fixed point. It's passing through a fixed point of a previous flowing fluid particle. So all these fluid flow pattern, if you like to describe mathematically, or if you like to understand, then you need to know certain definition. Number one thing, streamline. Then you need to know what is the stream tube, what is the path line, and what is the streak line. Okay, that you need to know. Any question? Anyone? No? Hello? No question? Okay. So what is the streamline? It's saying streamline is an imaginary curve or line through a flowing fluid in such a way that tangent to it at any point give the direction of velocity of the flow in that point. For example, you have a pipeline, but it is bent, like that. So your fluid particle is flowing along this direction, right? Is coming along this direction, and you can identify them with some arrow. So what will be the direction of velocity of fluid element at this point or at this point? How you can figure out? You need to draw a tangent line. If you'd like to figure out the velocity of the fluid element, right, this point, if you make a tangent line from this point, it will get direction of the velocity. If you like to figure out the direction of velocity right here, then you need to draw a tangent line. From the tangent line, you get the direction of velocity. Similarly, right over here is showing you like to get velocity right over here, then you need to draw a tangent. You want right over here, you need to draw a tangent. So it is an imaginary line that represent its tangent at any point and represent the direction of velocity. So pattern of flow field can be represented by series of streamline such that velocity vector at any point is giving tangent to the curve. So for example, a fluid element right over here, then is flowing along the streamline. And the streamline flowing along this direction. So we like to figure out that what is the relationship between a streamline and its velocity vector. So this fluid element traveling along the streamline, and it has its velocity is vector. So it has a three component: U, V, and W. This is the vector. The U is the velocity along x-axis, y-axis, and z-axis is W. Now, at a certain time, he was right over here, then came right over here. At this point, I like to figure out the velocity component. So you see, if you make a tangent, then this will be dx. This was distance. He traveled at time instance from here to here. He came from here, and along y direction he traveled this much, right? X direction dx this much, y direction this much. But this point, if this distance is dr from here to here, distance traveled by the fluid element is dr. So this dr will be a vector of dx, dy, dz. Okay, and the velocity component right over there is velocity is v. So v has three components, right? Y-axis v, along x-axis u, and z-axis w. So his vector velocity vector is this one. In that case, you see this smaller angle, this triangle, and this bigger triangle with the velocity is similar. From this triangular relationship, you can get this equation. Just remember, dx by u equal to dy by v equal to dz by w. And vector dr by vector v is same as this, all those components. Okay. Why? Because if dx proportional to u, because is dx is more, what does it mean? That means velocity component along x-axis is high. If the value of dy is more, what does velocity along y-axis is high. But there, if it's travel in a streamline, then their ratio dz by w, dy by v, dx by u will be equal to the dr by v. Okay. This is the definition of streamline. Other thing, stream tube. The streamline, then we have stream tube. What is the stream tube? And the mass of a stream tube is a imaginary tube to be formed by a group of streamline passing through a small closed curve, which may vary or may not be circular. There is no flow across the boundary surface of the stream tube, and velocity of the fluid has no component normal to the streamline. So what is the streamline? We are considering a group of streamline inside a tube, and it is a imaginary tube. And what is the condition? Condition is that the fluid element will always pass through the streamline, along the streamline, and there will be no flow along perpendicular to the streamline. That means fluid element should not flow along this direction, because as per definition, this is an imaginary tube, is always flowing along the streamline. And streamline may not be circular. So like this one, in the right side, it's a, if there is no flow across the bounding surface of the stream tube, velocity of the fluid has no component normal to the streamline. That means, and along the perpendicular direction, there will be no component of the velocity. What does it mean? It means that if you think along this axis is x and y axis is along this direction, that means the v will be always 0, no component of velocity along y-axis. But what will be velocity along x-axis only? So what does it mean? That means it makes a simplification in the calculation, in the software. Say, I like to figure out a flow pattern in a elbow. Elbow means this type of. So if fluid coming this and this way, it is getting out. How I can show or figure out the equation of the line from the flow pattern? If I think that fluid will flow along a stream tube, then I can describe this way, that fluid particle will flow along a streamline and in a stream tube. So although area over here is smaller, over here higher, but those streamlines are not intersecting, and fluid element is passing through the along the streamline. And this one, you can give direction in the software, and he will show you the streamline or flow pattern. So in that case, for example, you have this kind of flow right over here, like this one. So you see flow will be flow like that. So like so space between the streamline right over here is high because it is expanding. But still, uh, software will calculate that there is no velocity along perpendicular to the streamline. That means fluid particle will not travel, say one particle over here, in the next time, he will not go along other direction because y component is 0. His velocity will be always along the streamline. So this is steam tube is a imaginary tube. And we think that it's formed by a group of streamline where will be no velocity of the fluid particle along a direction perpendicular to the streamline. Okay. And why we assume just for simplification. Okay. Right now, it's saying mass flow rate passing through any cross section or slice of a given steam tube must remain shape. Shape of the steam tube changes from one instant to another because change in position of streamline, like flow through pipe, nozzle, diffuser, and two streamline can never intersect each other, as the instantaneous velocity vector at any given point is unique. That means your velocity vector along the streamline, always there is no velocity component along y-axis. That means velocity component along perpendicular to the streamline is 0. So that's why your fluid particle always flow through the streamline. And that's why you see right over here, the space between the streamline is less. That means they're shrinking. And right over here, space between the streamline is increasing. That means fluid is expanding, but still they are passing through a line. Now, how is they know this is the real problem or not? It depends on type of fluid, but at least you will get 90% or 95% close to the real situation in the computer software. And it's saying the flow through the streamline, amount of flow, say right over here, flow is 2 liters per second. Right over here will be same amount, 2 liters per second. Right? Because whatever, but right over here, velocity will be slow, over here, velocity will be high. But both cases, there will be no velocity along perpendicular direction to the flow. So our time is over, I think, right? So far, any question? Anyone?